Hello everyone, welcome to this video. Today we are going to study the periodic table, and also today is 15th August, that is the 75th Independence Day of India. So happy Independence Day to everyone who is watching the video. Now let us begin with the topic that we are intending to study, that is the periodic table. So the periodic table in its early times, it was the efforts of many scientists to arrange the elements in a proper way just to make study efficient, and it was done by early scientists like Dobereiner, like Newlands, like Mendeleev. First attempt was made by Dobereiner. What did he say? He said he arranged the elements in a chart, that is 3 elements at once. Okay, and then he said that the middle elements atomic mass will be the arithmetic mean of the other 2 elements of the triad. It was successful, but not for all. In some cases, it was seen that it was anomalous, so it was rejected. And moreover, the total elements, like it was 56 around something, but only few elements could be arranged in triads. Rest discarded. So that was the failure. Next comes Newland's laws of octaves. Newland's law of octaves, it stated that if the elements were arranged in increasing atomic mass, then the property will be repeated at every 8 elements starting from any element. But this was, again, there was a limitation. It was limited to atomic number 20, because beneath 20, beneath calcium, it was not possible. Beyond calcium, I mean, it is not possible. Okay, the last person who gave was Mendeleev's periodic table. Mendeleev was a Russian physicist, and he gave this periodic table, which is the base of current periodic table. He said that the physical and chemical properties of an element is the periodic function of its atomic mass, and atomic mass is what we are not considering today. We have today considered atomic weight as not the function of periodic property, but it is basically your atomic number, that is the fundamental property that will be considered today. So it was proposed by Moseley, that is Henry Moseley. Now let us get into the modern periodic table. In the modern periodic table, as you can see on your screen, there is a modern periodic table. You have seen that this side there is a row and this side is a column. So row column arrangement of elements is there in the periodic table. Now in the row column arrangement, like this will be formed. So this particular structure will be called a period, while this particular structure is called a group. Often this gets interchanged in our minds, that is, this becomes a group and this becomes a period. But actually this is a period, this is a group. Okay, so the columns are groups and rows are periods. Now in the modern periodic table, there are total of 18 groups, and 7 periods. 18 groups, 7 periods. There are one confusion that happens is, that is the lanthanide and actinide. Lanthanide and actinide sequence. They are located at the below of the periodic table. That is accepted, but they are not separate periods. Why? Because lanthanides, they belong to the 6th period, while this person belongs to the 7th period. So they are belonging from one period, they are not a separate period. That is the factor that is leading here. So that gets some confusions over there, but it's okay. Next coming is the different regions of a periodic table. What are the different regions of a periodic table? Regions. So regions of a periodic table. Now main region is, there are 3 regions. 3 particular regions are there. Number 1 is main group elements. Number 2 is transition elements. And number 3 is inner transition elements. So these are the main 3 groups that you are supposed to do. So these are the main 3 regions at a periodic table. Now main group elements are supposed to be 1, 2, first group and second group, that is alkali metals and alkaline earth metals. And again from group number 13 to group number 18. This is the main group. Now the left out groups, what are the left out groups? That is your 3 to 12. They are falling under transition metals category. That means gradual transition of metals to non-metals. That is why we are giving it as transition metals. In our transition metals, they are the series of lanthanides and actinides. Lanthanides, actinides. So these are the basic three regions of a periodic table. Blocks are different. Blocks are S, P, D, F, but regions are three regions. Okay. Next one is, why exactly have we named this periodic table as periodic table? Why not as any something else? It could have been elementary table. It could have been element table. Why periodic table? So there is a factor behind that. What is that? That sole factor that is behind that is the term periodicity. The term periodicity. The term periodicity is basically meaning something that is repeating at particular interval. Now since we are dealing with periodic table, we are limited to periodic property. So we will be defining as property, in terms of property that is being repeated at some particular interval. Okay, so repeat interval. So these are the few things that should be there in the definition of periodicity. Here, that should be there in a definition. So property that repeats at some particular interval is called periodic property, that is there in your syllabus. This is periodicity. Okay. Now, the different groups and different periods that are there. Different groups. Now there are a lot of groups, but we are not going to study all the groups. Which group we are focusing on, emphasizing on? Group 1, group 2, group 17, group 18. Rest are there. They are important, but not now. Okay. First group is group 1, alkali metals. Group 2's name is given is alkaline earth metals. Group 16, that is oxygen family, has been given the name chalcogen because they form ore. Metallurgy you have read definitely. And in the group 17, it has been told halogens because they form salts. And group 18 is inert, so it is an inert group. That is group 0, inert group, or noble gas group. Done. Now moving on to the periodic property. Periodic property, the property that will gradually be changing. Now before moving on to the periodic property, the basic change that is being changing is your basic change. What is that? Valency. Valency of a element. If you have ever seen a periodic table properly, then the valency gradually increases, coming back decreases. How? Suppose let's take the first period. Lithium we have, then we have beryllium, boron, carbon, nitrogen, oxygen, chlorine, neon. First period. Now check. This case valency is how much? 1. This case 2. This case 3, 4. This is not 5. Nitrogen is not 5. Again 3, 2, 1, 0. So what happens? This to this increases. Again this to this decreases. So valency first increases, then decreases across a period. But if you go with a group, like if I am taking lithium group, then lithium, sodium, potassium, rubidium, cesium, then all of them, they have got 1 valency each. So valency is not going to change across a, down a group. Across a period, first increases, then decreases. See here, 1, 2, 3, 4, 3, 2, 1, 0. That is how it is changing. This is valency. Now what exactly is valency, you know? Valency is, suppose there is an element A, it has got, suppose let us take 2 electrons in the outermost shell. So it can lose these 2 electrons. So this is valency. How much electron it is lost. And suppose let us take another element is there, that is having 1, 2, 3, 4, 5, 6 electrons in outermost shell. So these 2 electrons can be gained by this element. So that is again valency of that element. That is how much electrons it can gain. Let us take another element C is there that has 4 electrons in the outermost shell, and this electron also has 4 electrons in the outermost shell. Clear? This atom I mean, sorry. So 2 electrons and 2 electrons. So this also needs how many electrons to complete its octet, and this also needs how many electrons to complete octets. You have to check that. So in that case, may happen that these 2 electrons are shared. May happen that these 2 electrons are shared. So in that case, that is also the valency, how many electrons are shared, and that is called covalency. That has been given a name, that is called covalency. That means how many electrons are shared. More details are in chemical bonding. Okay. Now moving on to the primary factor. The periodic property is primary factor, upon which we will be learning the next periodic property, that is atomic size. Atomic size. Now atomic size is basically the size or the radius between the nucleus and the outermost shell. Let us take, this is the nucleus and this is the atom. Entire atom is this is the nucleus, this is the outermost shell. So from this point to this point, whatever lies the distance, that is the distance is r, then r is the atomic size. Right? Now an atom's size is definitely not 10 meter. Right? So atom size is very small. It is very small. 10 to the power minus something, minus 6 or minus 20, it can be there. Very small size. Okay. So in that case, radius cannot be written in meters. Can it be? Then it will become 0.0000000 something meter. That is a very hectic way of writing. So instead of writing r something in meter, we use the unit this is angstrom, or we use the unit pm, not pm. That is picometer. Picometer is written as pm. It's not that pm what you're thinking. It's now is 1 pm. It is not like that. So it's picometer. Relation between SI units. 1 meter is equal to how much picometer you have to remember? 1 meter is equal to 10 to the power minus 12 picometer. Am I right or am I wrong? Wrong. Why? Because in this case, we are going to write the opposite. Why? 1 meter is not equal to 10 to the power minus 12 picometer. But 1 picometer is equal to 10 to the power to minus 12 meter. That is where in writing relations, mistakes are often made. So how to write that? 1 picometer is equal to 10 to the power minus 12 meter. Not the vice versa. Then it will go wrong. Similarly, for the another case, that is for this case, angstrom case, that is 1 angstrom is equal to 10 to the power minus 10 meter, and not 1 meter equal to 10 to the power 10 minus 10 angstrom. That is wrong. So these are the two relations that is necessary. Though calculations are not there right now, but this is the relation that is to be used for this. Now this is atomic size. Now what is the trend of this atomic size in the periodic table? Okay. First let us take lithium and let us take boron. Lithium has got 3 protons attracting 1 electron, and this bothered with the valence electron. And here for boron, there are 5 protons that is attracting your 3 valence electrons. So power in this case is greater, but size will approximately decrease. Okay, why it will decrease? Because 5 proton can attract 3 electrons more closer than 3 proton will attract 1 electron. Please see this. Okay, so nuclear charge goes on increasing, so size goes on decreasing as nucleus more tightly attracts the valence electron towards itself. Okay, so nuclear charge goes on decreasing. Now again there comes an exception. What is the exception? One small exception is there, that is, suppose I am writing lithium, there is beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. This was supposed to be. This is expectation. 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 This. Reality is not this. What is the reality? Reality. Reality is, check the reality. NO NEF. This is the reality. So what change is being seen? This is coming here, this is going here. Right? Why is it happening? It is because this any, not only any, but anything can be possible over there. Any noble gas, I mean, they have complete octet. So electron-electron repulsion will take place. So that electron-electron repulsion to some extent it overcomes the nuclear pull and it becomes greater than in size the preceding halogen. Not this element, but only the preceding halogen, it will be greater than size. So it comes before the preceding halogen. This is an exception that we have to remember from this part. It is across the period. So across the period it is decreasing, summarizing the entire thing. So across the period this has to decrease because nuclear pull has to increase. Electrons more closely pulled towards the nucleus. Exception lies here, that is the noble gas due to maximum electron-electron repulsion, its size is greater than the preceding halogen. Okay, now next is down the group. Now what happens to the atomic size as you move from up to down the group? What happens? So down the group, that means you are moving up to down, not up to bottom, whatever you say. Down the group. So I have already said that whenever there is an increase either this side or this side, then the opposite has to be decreased. So it was decreasing across a period, so here it has to increase. So it increases. Now why does it increase? Now this is a common question. So let me write lithium Na. Okay, so this has got 3 protons attracting 1 electron and this has got 11 protons attracting 1 electron. So definitely this power is more. So if this nuclear charge is more, then it should have been like this, but reality says this. Why? Based on the nuclear pull factor, if we see, then this should be smaller in size than lithium, but it is not the case. Why? Why? Because when we move down the group, shell add on. Shells add on. So if shells are adding on, then nuclear charge power has to decrease. In physics you must have read that if it is in, suppose from here a force is produced, so the force will act within a particular range. Beyond that range the force is not acting. Similarly, some concept of this is also being applied over here. Specifically, if I say there is a term that is called shielding effect. Shielding effect. This shielding effect reduces the nuclear pull on the valence electron due to preceding shells. So this is basically shielding effect. So due to shielding effect, this Na has got a greater size than Na. But you cannot write shielding effect in class 10. So that is not going to be done. Then what logic will be applied? The simple logic that we have to apply is that Na's size is greater. That means number of shells is increasing. So nuclear charge factor, okay, nuclear charge factor and shell number factor, 2 factors are acting. One is nuclear charge factor and one is shell number factor. Next you have to remember the shell number factor dominates. This is the important thing. Whenever there is a conflict going on, then the shell number factor we have to dominate. You check here. So here check. Sodium has got 3 shells. Sodium has got 3 shells. This has got 2 shells. So whose shell is more? 3. So sodium will have greater size than lithium. So this is the thing that you need to remember. So summarizing again, down the group, atomic size has to increase. Why? Due to addition of new shells as you move down the group, and due to the dominancy of shell factor over nuclear pull factor. Next is not metallic character. Before that also many things are there. That is the size of a cation, size of an anion and isoelectronic species. Now cation. How is a cation formed? A cation is formed, suppose this is an element. If this element loses n number of electrons, then this will form n number of positive charge. So this is a cation. So now see, suppose A had initially suppose let us take it had 2 protons. Initially let us take it has 2 protons. Now also it has 2 protons. Initially it had, let us take 2 electrons. So here let us write 2, here let us write 2. And now it has how many electrons? 2 electrons it has lost. Let us take here it has lost 2 electrons. So if it has lost 2 electrons, then it is now A 2 positive. Okay, let us take this is 2 electrons. Cation. Let us write now cation. Now check, in case of cation, let us take this is an element A which has lost 1 electron to form 1 positive charge. It has 2 protons, not 2 protons, it has 11 protons, it has 11 electrons in total. Now it has got 10 electrons and 11 protons. Okay, now see, 11 proton attracting 11 electron. This is you already know. And here 11 proton attracting 11. Who will have greater attracting power? This or this? This is equal. This is equal. Okay, but this is not equal. This is unequal. So proton dominates. So if the charge of proton nuclear pool is dominating over the electrons, that means it will be held more closer. So size of A will be greater than that of A plus. So size of cation is always less than that of the original parent atom. Okay, why? Due to the deficit of electron. There is a deficit of electrons. This electron is less, so it is more closely attracted. Now the opposite happens in case of anions. What is that? If let us take this is having 17 protons, this is gaining 1 electron, so 17 electron, here it now becomes 18 electron and 17 proton. So previously, let us take, previously 17 was attracting 17, now 18 is 17. Now see, 18 electron and 17 proton. So proton is not dominant, electron is dominant. So as a result, what will happen? One electron will flutter here and there. So what will happen? A size will be less than A minus size. That is what is the concept. So anion size always is greater than the parent atom, while the cation size is less than the parent atom. So this is the structure. In middle has to be the atom. Cation charge has to be, cation has to be here, sign is like this, anion has to be here, sign is like this. Next is isoelectronic species. Isoelectronic species. Isoelectronic. Now this word isoelectronic, iso means same number of electrons. So electron number has to be same. So that can be neon, that can be sodium plus, that can be Mg double plus or Mg2 plus, and going on this side also, that can be your fluorine minus, then oxygen 2 minus, nitrogen 3 minus, and aluminium 3 plus. Okay, so all this will have the same number of electrons, is 10. So all of these are 10 number, but the size is same for all? No. Why? Because cations are smaller and anions are greater, and this is in middle, this has to be in the middle, while these are smaller, this is greater. Now you have to arrange properly. How will you arrange? Which one is greater, which one is smaller? It is basically the nuclear pull factor that will be most important for here. Now let us do one thing. Suppose there is your given is Na positive and you have F negative, and you have this Mg2 positive and you have this O2 negative. Okay, now let's check who has better size or smaller size. Na plus, how many protons are there? Proton is remaining same, that is not going to change with ions. But instead of 11 electron, there is 10 electron. Here electron is remaining 10. Electron remains 10, but proton is 12. Here in this case, proton is 9, electron gets 10 electron, but proton gets 8. Now check who will have a greater nuclear power. Here 10 electrons, 11 is attracting 10. Cation cannot get the mass. First you have to check this, because this will be greater than the, of course. So F minus is 9 and 10, and this is 8 and 10. So 8 can attract 10 better, or 9 can attract better. So greater will be the nuclear charge, smaller will be the force. Who has greater number of proton? 9. So 9 can attract 10 more than 8 can attract 10. So it is fluorine ion, that is fluoride ion, whose size is going to be less. So it's F minus, then comes O2 minus, then without it. Okay, if you are in decreasing order, bigger to smaller. So it's actually the nuclear pull factor that is going to depend. Here 10 is attracting 11 and 10 is attracting 12. Who has the number put on this? So Na plus size will be more than that of Mg2 plus. But here F2 minus size will be greater than F minus. So in case of minus, what happens is as you go increase with the charge, here also charge is increasing, but size is increasing for this. So as charge increases for cations, size decreases, but here size increases as charge increases. That is also a factor you can use to just arrange the elements. Okay, so in this case what will happen? Na plus, then Mg2 plus, then L3 plus it comes, that also will go up, but Na plus, Mg2 plus there. So 1 plus, basically the logic is plus, then 1 plus, then 2 plus, whatever is there. Okay, and for anode it has to be 2 minus, it has to be 3 minus, 2 minus, minus 10. Okay, this is the logic for atoms. 3 minus will have the greatest size, 2 minus less, then minus less. So here the same thing. And for cation, plus greater, then 2 lesser, 3 more lesser. So it's the opposite for vice versa. So that was all I have to say from atomic size. In the next video, we will be talking about metallic character and non-metallic character. That's all for this video. Hope you have enjoyed watching the video.